All right, so this is the last part of 1.6 absolute value equations. We have the absolute value of 2x minus 3 equal to 11. So in the red is how we will set up solving our absolute value equations. So remember, whenever you're trying to solve, you want to know when is this statement true. And so we want to know when is 2x minus 3, the absolute value of 2x minus 3 equal to 11. So the way we will set it up is that we will set what's in the absolute value equal to 11 and then set it equal to negative 11. Why? Because when this is 11, the absolute value of 11 will be 11. But also when this is negative 11, the absolute value of negative 11 will be 11. So you always, when setting up your absolute value equations, you would take what's in the absolute value, set it equal to the number that you see, and then set it equal to the opposite. In other words, the negative. All right, so that's what we'll do. Let me erase this so we can walk through it. So you have 2x minus 3 equal to 11, positive 11, and then 2x minus 3 equal to negative 11. So from there, this was just about setup, because from there you will go ahead and add 3 to both sides. And then you have 2x equal to 14 divided by 2. X is equal to 7. Then on the other side, you have 2x equal to negative 8 divided by 2. X is equal to negative 4. All right, make sure we're okay before we go to the next one. All right, so next one we have 5 times the absolute value of 1 minus 4x minus 15 equal to 0. So you see in the red, I wrote a note that we need to isolate our absolute value. So in other words, we want to get this absolute value quantity by itself on one side of the equation. So we'll have this same setup that we had initially with the absolute value of 2x minus 3 equal to 11. So we want to get this by itself. So we'll add 15 to both sides. And that'll leave us with 5 times the absolute value of 1 minus 4x equal to 15. All right. Divide by 5. And that'll leave us with the absolute value of 1 minus 4x equal to 3.
I have a question.
Yep.
Okay, so you know how you divided this one by 5?
Mm-hmm.
How come you didn't just do the setup like we did the last one, where you take the 2 separate? Like, you know what I'm saying?
Mm-hmm.
Oh, how?
Wait, when you talking about like we did here and had the 2 separate ones?
Yeah, why didn't you do that with that one?
Well, we're gonna get to that. We're about to go there next.
Oh, okay.
Yeah, but we need to set it up like this so we'll have just the absolute value on one side. Then we'll do that step.
Okay.
Good question. Good question. All right. So let me erase this. So yep, like she mentioned, that was our next step. We set 1 minus 4x equal to 3 and 1 minus 4x equal to negative 3. But what was key to what she asked is that we had to have our absolute value expression. set on one side of the equation by itself before we can set it up into our two pieces. So yeah. And then from there, we go ahead and solve. Oh, see, we got a question. Yep, we had to get rid of the 5. Yep, so we divided both sides by 5. So going back to the original, we moved the 15 first, and then we moved that 5 and got our 1 minus 4x by itself on one side. Then from there, we subtract 1 from both sides of our equations. 1's cancel. That'll be negative 4x equal to 2, and negative 4x equal to negative 4. Divide by that negative 4, and we'll have x equal to negative 1/2, and x equal to 1. All right. Questions? Any questions? All right, next one. So I want us to be careful here. Here we have the absolute value of 3x minus 7 equal to negative 21. So remember, whenever you're trying to solve an equation, you're supposed to be asking yourself, when is this equation true? Or in other words, in this case, when is the absolute value of 3x minus 7 equal to negative 21? Don't forget, whenever we apply the absolute value to anything, the result will be positive. So you're asking yourself, when is the absolute value of 3x minus 7 equal to negative 21? The answer is never. The answer to that question is never. So the absolute value of a number is negative, if I can get it right, never negative. Since that is the case, the answer is no solution. So be careful with that, because if you get in your flow, you start getting into your mode and you don't take note of that negative, it's easily just get in the flow and just do stuff. But you can apply a lot of calculation to this and you're going to get the wrong answer, because there is no calculation here. Just observation and then application. You recognize that the absolute value is set equal to a negative number. The absolute value can never result in a negative outcome. There you go. Can never have a negative outcome. So your result, your answer to your solution is that there is no solution. This can never be true. Never be true. All right. And once again, you always have to make sure that you're making this comparison with your absolute value quantity isolated on one side of the equation. You know, so you always want to solve for that first before you make this declaration. Because if I had negative, let's say negative 5 on the outside of that, if I divide by negative 5, the result is no longer negative, because negative of negative will turn positive. So then you'll be actually able to do the problem. So just making sure you're careful on when you make this, you know, deduction. All right. So that's it for 1.6. Questions on that before we go to 1.7. Excuse me. All right. Let's look at 1.7. So 1.7 is linear inequalities and absolute value inequalities. All right. Linear inequalities and absolute value inequalities. So up to this point, we've dealt with equations. So now we're looking at inequalities. And let's look at the difference between the two. Your linear equation. Of course, we had quadratic equations as well, but we're just comparing linear to linear right now. Linear equation compared to your linear inequality. Well, the first thing is that one has an equal sign. The other has an inequality symbol. Then the next thing we'll notice that when we solve inequalities the same way we would our equations. in which you will subtract 2 from both sides. Here we have x equal to 2. That's only one solution. The only solution is 2. 2 plus 5 is equal to 7. Now, when you're looking at your inequality, you're going to have a solution set because you're going to solve and it's going to be x is greater than 2. So any value that's greater than 2 will make this a true statement. So in other words, you're talking about what values can I plug into this left side, plug in for x, that will make the left side greater than the right side. So if I had 2.1, plug in 2.1 for x, that's 2.1 plus 5, which is 7.1. 7.1 is greater than 7. If I had 50, 50 plus 5 is 55. 55 is greater than 7. If I plug in 1 million, that will still make the left side greater than the right side. So you want to know what are all the values that can make that left side greater than 7. And there's an infinite amount of values that will do so. And that would mean that will be your solution set, all the values that are greater than 2. So that's going to be the main differences between your linear equation and your linear inequalities. Give you a chance to write before I scroll up. All right, so let's scroll up to our inequality symbols. So we have less than or equal to, greater than or equal to, will be the symbols that we use for our inequalities. All right. All right, so we saw one piece of our solution. We saw down and have our solution set, but there are 2 other pieces to our solutions that we could use, to represent what is a solution for us. So we could graph it, or we also can represent it in interval notation. So the symbols, as far as parentheses and brackets that we will be using, whenever we have less than or greater than involved, we will be using parentheses. And that means we will exclude the value that's being represented at the time. We'll talk about what that means in a second. We can have less, if we're using less than or equal to, greater than or equal to, we'll use the bracket. That means we will include it. And then parentheses will always be attached to your infinity symbols. Negative infinity, positive infinity. Can never include infinity because you always can go to the next number. All right. All right, you want to scroll up? You say after this section, okay. So let's go ahead and copy this, then I'll scroll up. So examples of what I mean by including and excluding the values. If I'm looking at x is greater than 2, we're talking about all the values that are greater than 2. That means 2 is not included as a part of the solution set. So in other words, it's excluded. You want all the values that are greater than 2, but 2 is not used. If you're talking about greater than or equal to 2, then that's all the values that, greater than or equal to 2. That means 2 is included as a part of the solution set. So one excludes 2, the other one includes 2. And what these 3 pieces will represent each other when it talks about the solution set. And you can see one and know what the other one says versus what the other one doesn't say. All of it is connected. So all you need to do is see one piece, and that will represent the other 2. and that goes for the graphing solution set or the interval notation. So each one should represent the other and say the same thing. So trying to give you guys a chance to write, just kind of filibuster in a little bit.
We are going to talk about when we're graphing it. We are going to talk about when when we graph it, the circle has to be empty or filled up, right?
Well, those take the parentheses and bracket takes the place of that.
Oh, okay.
Yep. Good question. Good question.
All right.
Um, and so this represents open circle. This represents closed circle.
Oh, so, okay. All right.
Yep. Same meaning, but because we use an interval notation, this translates all the way throughout versus just use open and closed circle.
Okay. All right.
So someone asked me to scroll up. I don't know where you wanted me to scroll up to. I don't know how far up to go. All right, I don't hear from you, not hearing from you. So, okay, there we go. Oh, you say you good? Okay, cool. All right, so number line just right here, just making sure we're clear on that. We're just talking about a generic straight number line. If you look at it, number one, everything to the right of one is greater than it. Everything to the left of one is less than it. Same thing with the negative two. Everything to the right of negative two is greater than it. Everything to the left of negative two is less than it. So that will always be the case no matter what number you're dealing with. Everything to the right of it will be greater than it. Everything to the left of it will be less than it. So just going back to x being greater than 2 or x being greater than or equal to 2, using those solution sets and seeing how that, those three parts coincide and how they reflect each other. If I'm looking at the first one, x is greater than 2, you will use parentheses over the 2 and shade to the right. That will be your graph. Then for your interval notation, that third piece, notice it's going from 2 to positive infinity. And so that's what I wrote, 2 comma infinity, parentheses over both. All right, looking at the next one, x is greater than or equal to 2. The relationship as far as shading is still the same. It's just that we use a bracket instead of parentheses because of the or equal to symbol. And the same thing goes for the interval notation. Still going from 2 to infinity. We use bracket over the 2. And don't forget, you will always use parentheses on your infinity sign. All right. Questions before we look at a chart that uses or shows us all of our scenarios? All right. So notice in red, it says that A and B are real numbers. So A and B is just going to represent generically what can happen no matter what goes on. Just like if you look at the first two rows, those are reflected with that x is greater than 2, x is greater than or equal to 2. Notice the relationship is still the same, still shading to the right using parentheses and brackets. So that's what we're looking at in the first two rows. X is greater than A, put parentheses over the A, shade to the right, interval notation, A comma infinity with parentheses. X is greater than or equal to A, same relationship as that, except you're going to use bracket over the A in both cases. Now in the second two, we're talking about being less than A. So where before we shaded to the right, and the next two will shade to the left, using parentheses for the greater than symbol, bracket for the, I said parentheses for greater than, I meant parentheses for the less than symbol, and bracket for the less than or equal to symbol. That's what we have sitting over our A. And then be careful. Here we read our graph from left to right. We're coming from negative infinity to A. So that's how we represent it here in our interval notation. negative infinity to a, and parentheses over both, but then the next one bracket over the a. So generically, that's how all of them will be set up as far as our first 4 scenarios, no matter what the numbers are. Give you a chance to write that before I scroll up to the next 4.
Professor Tucker?
Yep.
For the third one, where x is less than a, it's going towards the negativity. The arrow is going towards the left side, towards the negative side, right?
Yes.
So from point A to negative infinity.
Well, the way you read it is from left to right, though. So you're really
So
saying negative infinity
to
to
A.
a.
Okay, but you get it the way I said, like.
Yeah, I just wanted to make sure. I didn't know if you were going somewhere with this, so we know with the interval notation. But yeah, that's what you're talking about.
All right.
And so, like, 'cause some people have written the interval notation as a to negative infinity, and so I just wanted to, I didn't know if that's where you were going with it or not. So, yeah. Okay, next 4. Here we have 3-part inequalities, and we'll talk about that, of course, before we close out solving your 3-part inequalities. Notice your variables in the middle, and you're talking about the values. Your solution set will be the values that are greater than a, but less than b. So that will be shading in between a and b. So that first one in this scenario, you have parentheses over both a and b. The second one, bracket will be over the a, parentheses over b. That third one, parentheses over a, bracket over b, and then that final one, brackets over both. And then in your interval notation, that same thing, that same symbolism will be reflected. You're going from a to b, a comma b, then we're using parentheses, parentheses, bracket, and then bracket. All right. All right. Any problems? Can I scroll
Could
up?
you just leave it on there for a couple more seconds, please?
Yep, not a problem. Let me know when you finish.
Okay. All right. Thank you, Professor Tucker.
Not a problem. Not a problem. All right, so there's one thing we have to consider when solving linear inequalities that we didn't have to when solving regular equations. Remember, everything else is going to be the same. Use opposite operations and all the good stuff. But when it comes to linear inequalities, if you have to multiply or divide by a negative number, then you must change or flip the inequality symbol. So that's the one thing you have to consider that you don't have to when you're dealing with equations. If you're going to multiply or divide by a negative number when dealing with inequalities, you have to flip, the inequality symbol. Some people say flip, and basically you're changing it. If it's greater than, you'll change it to less than, but if it's less than, you will change it to greater than. right, simple example of that is if I have negative 3x is greater than 17, I would divide both sides by negative 3 in order to solve, and that greater than changes to less than after I divide both sides by the negative 3. So my solution set would be x is less than negative 17 over 3. And then for my graphing, I shade to the left using parentheses. My interval notation, negative infinity to comma, negative infinity, comma, negative 17 over 3, use parentheses over both. All right, so let's say go up to the beginning of this definition. Yep, give me 1 second. All right, so I think that we're talking about. All right, are we good? Let me know. All right, cool. All right, so let's look at solving. So we have 3 minus 2x is less than or equal to 11. So first thing we'll do, we're trying to get x by itself. So the first thing we'll do is subtract 3. 3's cancel. That leaves me with 2x is less than or equal to 8. Then we'll divide by negative 2 here. And the result will be x is greater than or equal to negative 4. So don't forget, once again, we divided by a negative. So that less than goes to greater than. And we have x is greater than or equal to negative 4. So as far as our graph is concerned, we shade to the right when the values that are greater than negative 4, but we use bracket because of the or equal to symbol, and then interval notation, negative 4 to positive infinity, bracket, and parentheses. All right. Everybody okay? All right, next one. X plus 3 over 4 is greater than x minus 2 over 3 plus 1 over 4. So just like before, when we're dealing with this type of problem, we want to find the LCD. And that is 12. And so we multiply each numerator by that 12. 4 cancels into 12, leaves you with 3. 3 cancels into 12, leaves you with 4. 4 cancels into 12, leaves you with 3 again. And that gives you the result at the bottom. 3 times x plus 3 is greater than 4 times x minus 2 plus 3 times 1. So now we distribute. Distribute the 3, distribute the 4. That'll be 3x plus 9 is greater than 4x minus 8 plus 3. And the negative 8 and the positive 3 will add together to give us negative 5. Now your goal should be to get your x terms on one side, other terms without x on the other. I'm going to bring my 3x to the right just because I'm trying to emphasize something. So I cancel out the 3 on the left and cancel out the 5 on the right. And that'll give me 14 is greater than x. But my math lab more than likely wants the x on the left side. So if you need to flip your stuff or flip your expression, just make sure that, you know, if the mouth is open towards the 14 here, that is open towards the 14 on the other side as well when you flip it. You just have to be, you know, consistent with the flipping of your expression. But
where did 5 come from again?
You said the 5? I think you said the 5. That came from negative 8 plus 3 right here.
Okay.
All right. All right. So now we have the other two pieces. We're talking about values that are less than 14. Shading to the left of 14, use your parentheses. And then interval notation is negative infinity to 14, parentheses over both. All right, any questions?
Did we add 5 first before subtracting 3x?
I did them pretty much at the same time. It doesn't matter. Either way, you get the same result. The main thing here was that I subtracted 3x so that it would cancel out on the left, and I added 5 so that it would cancel out on the right.
Okay. So is that for like just this problem, or does that happen a lot with these type of
What you mean by that?
like, could we subtract x and just the like how you did negative 3x plus 5 on both sides at the same time?
Oh yeah,
Does
you can
that
always
happen?
do that. Yeah, normally I just do them in one step just to make sure everybody's with us. But you know, at this point, I'm assuming that you guys, you know, are cool with the, you know, moving things over across, you know, by using opposite operations. So I just did 2 at the same time.
Okay.
But you can always, yeah, if you want, you can always do them, you know, at the same time. You know, it won't hurt anything at all.
All right. Thank you.
Uh-huh. All right. Says y is x less than 14. All I did was flip this because my math lab will normally want your x on the left side. So when I solved this, I had x on the right side, and that may happen when you go throughout your solving. But if my math lab express upon you that they want X on the left, then you have to flip your expression. And so I was just emphasizing that that may be the case. So I was just showing you that we didn't change the relationship. All we did was write X on the left side versus X being on the right side. So notice the mouth is still open towards 14. So we didn't change the relationship. So hopefully that answered your question. If not, feel free to say, no, I didn't do it. Let's see. Okay, cool. All right. So 3-part inequality. Remember I told you that was the last 4 scenarios in that chart where you have 3 parts to your expression. You have this, this, and this, where normally you only have the 2. But your goal is to get X by itself in the middle. So you need to solve your equation or your inequality while leaving X in the middle. So you follow the same procedure that you would normally do. If you're trying to solve for X, it's just that now you're going to subtract 1 from 3 parts instead of just 2. The ones cancel in the middle, and that'll leave you with -4, 2X, and 2. Then divide both sides, or each part, not both sides, by 2. Because once again, you're trying to get X. Let me do that. Once again, you're trying to get X, by itself. So you divide by 2. And the result would be X is greater than -2, but less than or equal to 1. All right. Then we have our 2 other pieces. Remember, those are the values that are greater than -2 but less than 1. So you shade it in the middle, bracket over 1, parentheses over the -2. Well, you're moving the 1 to all 3 pieces because your goal is to get X by itself. So you need to start isolating the X. So you start doing the opposite operations to whatever expression is applied or whatever operations are applied to the X. So the first thing we did was subtract 1 from all 3 parts so that the 1 could cancel and give us just 2X. And then your goal is still to get X by itself, but we still have a 2 attached to it. That's 2 times X. So we divide by 2. And the whole goal is to get X by itself. So you're doing the opposite operations of everything that's being applied to the X. So notice we didn't look at, moving this 4 or moving this 2, because those things are already isolated from the X. We want to get everything away from the X. So that's always your goal when you're going to solve. Move whatever is attached to the variable. All right. Any other questions on that? Then we got one more. Yeah, we got one more topic in 1.7, and then we'll be done with it. Yep, not a problem at all. Okay. Absolute value inequalities. We're going to let U be an algebraic expression and C be a positive number. That's going to be key when we look at the final example. C is a positive number in these relationships. So if you have the absolute value of U is less than C, so the way we will set it up is by what's in that purple box. You would do U is greater than -C, but less than C. But if it says greater than, You know, we're looking at this right here. If it says greater than, we'll use what's in the green box for our setup. We would do x is less than negative c, or u is greater than positive c. So once again, if our symbol is less than, we'll use this setup. If our symbol is greater than, we're going to use this setup down here. And also, you see in the red, the same thing goes for when we have or equal to symbols.
Professor Tucker,
Yep.
you say that one more time?
When we have the less than symbol, we'll use this setup. When we have the greater than symbol, we'll use this setup. And it's all going to be set up according. It's all going to be based on what symbol we have initially.
Okay.
So, yeah.
Thank you.
Say again?
Thank you.
Oh yeah, no problem. And so you'll see when we actually put the stuff to it, the actual examples, you'll see what I mean. Giving everybody a chance to write. All right. Can we try it? So first one, we have the absolute value of x minus 4 is less than c. I said less than c, less than 3. So look at our initial setup. We have x minus 4 is greater than negative 3. X minus 4 is less than 3. So in our, not example, but in our format, notice they have absolute value of u. So that means x minus 4 represents u. And then that c is represented by 3 in this case. And so that's why we have that negative 3 on the other side. And we're using the positive 3 that we have initially with the x minus 4 in the middle. Once again, we have the less than symbol here. That's what tells us to do this or use the setup. So before we go to solve it, questions on what we've done. So we have a 3-part inequality. To solve, we'll add 4 to all 3 parts and have the result of x is greater than 1 but less than 7. All right. Questions before we do the next one? All right, so this next one we have 7 is less than the absolute value of 5 minus 2x. So don't forget, when we go back to our setup and how they tell us to set up, our absolute value is on the left side. So if I wanted to rewrite this expression being on the left side, once I did so, I have the absolute value of 5 minus 2x on the left side. Well, that means if, once again, if the mouth is open towards it initially, if I just flip it, then the mouth still should be open towards it. When I flip it, putting my expression on the left. So that means we have a greater than symbol here. Since my symbol is greater than, I'll set it up this way. 5 minus 2x is less than negative 7. 5 minus 2x is greater than 7. Once again, it's the greater than symbol that told me to do this.
I have a question.
Yes.
Are we flipping it so we get x in the middle?
Now, are you talking about
The 2x?
this right here?
Yeah.
This expression? Well, we flipped it so we can make a clear comparison to what we had here. Notice that the absolute value was on the left side.
Mhm.
And so if I'm trying to follow with this whole setup, I
Okay.
need my absolute value to be on the left side of my inequality.
Okay.
And so that's why we did that. So so we did that, put that over here, and then that let me see, okay, now that I have my stuff on the left side, do I have a greater than or less than symbol? And we have a greater than, and that told me to do, you know, this down here. All right. So the real thing, the real challenge, I don't say challenge, but the main thing that you guys want to remember when having these is pretty much the setup. Outside of that, it's the same thing we've done as far as solving. Once you set it up, you subtract 5 from both sides in each case. I think I want my line to be longer. Subtracting 5 from both sides gives me negative 2x is less than negative 12, and negative 2x is greater than 2. Divide both sides by negative 2. And don't forget, whenever dividing by negative or multiplying by negative, we have to change our inequality or flip it. So it goes from less than to greater than. So that's why I have x is greater than 6. And then on the other side, it goes from greater than to less than. That's why I have x is less than negative 1. All right. So we have x is greater than 6. So you're going to shade to the right of 6. And also x is less than negative 1. Shade to the left of negative 1. And then my interval notation reflects the same thing. Talking about going from negative infinity to negative 1. Use our union sign. That's the same thing as or. And then 6 to positive infinity. Don't see what you want. All right. And do it one more time just to make sure we're good. But any questions?
Professor Tucker,
Yes, sir.
make sure I got it. Basically, you're doing the problem twice as a positive and as a negative.
Yes, sir.
And then your signs correlate to your answer.
Yes, sir.
I got
Yep,
it.
yep, yep. Yep, everything, all your signs are going to reflect each other. All pieces, you know, have to reflect the same thing. Yep.
That union stuff is getting complicated.
Now, with the union symbol, try not to make that more than what it is. Like I said, it represents or mathematically.
Union, but
Say again.
I misspoke. The let you thing was getting complicated.
Oh, say that one more time. You went out a little bit.
The let you was getting complicated.
Oh, yeah. Gotcha. I know what you're talking about.
I misspoke.
Yeah. All right. So let's do it one more time, and then we'll be good. So here we have negative 2 times the absolute value of 3x plus 5 plus 7 is greater than or equal to negative 13. So what we want to do here is, before we can, you know, split up stuff or write the opposite number and everything, we want to first make sure that we isolate our absolute value quantity. So the first thing we'll do is subtract 7 from both sides. 7s will cancel. And that'll leave me with negative 2 times the absolute value of 3x plus 5 greater than or equal to negative 20. All right, then we'll divide by negative 2. Negative 2's on the outside will cancel. But once again, we divide by negative 2. And so that means by, well, because we divided by a negative, that greater than will turn into less than.
Is this where the problem needs to be positive or it's not right?
Yes, that's always going to be the case, right? And so whenever dealing with your absolute value, it being compared to a positive versus a negative will mean all the difference in the world. And we're gonna that's gonna be the last thing we talk about. Just talking about what you can and cannot do. As a matter of fact, that's what's going on right here. For some reason, I got this in between my problems, so we're gonna skip that and come back to it. I think somebody asked me a question when I originally did these notes that made me discuss it. But so before we go to that negative thing or negative option, if we have a negative situation or outcome, let's finish this one. We have the absolute value of 3x plus 5 less than or equal to 10. So just follow my purple line, and we're still there. Absolute value of 3x plus 5 is less than or equal to 10. Once again, we divide it by that negative 2, and that's why I went from greater than to less than. And because it's less than, remember we said that if it's less than, then this is our setup. We have the absolute value of 3x plus 5 is less than or equal to 10. Because it's less than, I will put this on the left side of that expression. Okay. So now once we have our setup, once again, this is our setup, we'll subtract 5 from both sides. Subtracting 5 from both sides will give me this. We have 3x is greater than or equal to negative 15, but less than or equal to 5. And then we'll finish it by dividing both sides. I said both sides, each part by 3. And that will be your result. X is greater than or equal to negative 5, but less than or equal to 5/3. All right. Then we have our 2 pieces that reflect that solution set. Graphing, you shade in between, brackets over each part or each number, and then your interval notation, negative 5 to 5/3, brackets over each. All right, so before I scroll up, questions, any questions on that? All right, so going back to your classmate's question, great question. So don't forget, the result of an absolute value will always be positive. So if I look at asking myself, when is the absolute value of x plus 7 greater than negative 5? The answer is always greater than negative 5. So your answer is going to be all real numbers. So if you're doing the absolute value of a quantity and you're comparing it to a negative and you want to know when is it greater than negative 5, the answer is all real numbers. Now, if I want to know when is the absolute value of x plus 7 less than negative 5, the answer is never. That's never the case. So the result would be no solution. The absolute value will never be less than a negative number. because remember, the result will always be positive. So now don't forget, you can never make this declaration or come up with this deduction until you've isolated the absolute value quantity. That's why remember we had to solve for it, get an absolute value quantity on one side by itself. And then you can make your deduction or come to your conclusion. Once again, the absolute value is always going to be greater than a negative number. So that means any number I plug in will be true. It will never be negative, less than a negative number. So there's no value I can plug in for x to make it true. So my answer would be no solution. All right.
Professor Tucker,
Yes.
wait, what is this? X plus 7, which is less than -5. Where'd you get this?
Just examples.
Oh, this is just an example?
Yep, just an example explaining the scenario of comparing it to a negative number. So remember, up to this point, all the ones we compared them to were positive. Even if we go back to this, positive number.
Mm-hmm.
So I was just saying that this scenario, this stuff right here only refers to when C is positive.
Okay.
But if it's negative, there's no work to be done.
Okay.
It's just observation, of what you have.
Got it.
Mm-hmm. All right. Any questions? Questions? Make sure we're good before we close out today. Next class, I'm going to open up the floor. The whole class is dedicated to whatever questions you guys have. Not anticipating doing any new material next class. The floor will just be open for you to ask whatever questions you want. You can bring them to the class, bring them to the table. We'll just talk about them. So some questions may be generated over the weekend when you get into your My Math Lab work. So make sure you get in there. Even if it's just stuff you want to see me do again, just bring an example of something you just want me to do, even if you wasn't able to make an attempt at it. But next class will be your opportunity to ask whatever questions you want to ask during class time.
So our test isn't due on the 7th, right? It's due.
Yep, more likely it will be due on, let's see,
the 14th, because the 14th is the Sunday. You were talking about Sunday.
I'll probably do 15th since it's Valentine's Day. I won't hurt you. Won't hurt you guys on Valentine's Day.
Okay. So the test is due on the 15th, on the President's Day.
Yes.
So not on the 7th. I'll put that in my calendar.
Yep.
Do we have school on President's Day?
As far as I know, yes. I'll find out. I think we do. If not, I'll let you know. I'll shoot you guys an email. To confirm. But as far as I know, we still have class. Yeah. All right. So I have a few questions to answer. So I'll do that. If you want to stick around for those questions, feel free to do so. If not, you guys have a great weekend. Be safe. And I'll see you on Monday if we have class. If not, I'll see you on Wednesday. Have a good one.
Have a good weekend. Thank you.
Yeah, no problem. You do the same.
I'm here, Professor Tucker.
I know you're here, man. No, I'm just playing with you, man. Let me get this answer that's in the chat since it's right here. And then we'll get to that one you were talking about. It was 18I squared. And he asked if I had, will it be? Yes. That I squared simplifies to -1. I squared always simplifies to -1. And so, right, it'd be -18. Mr. Hill. All right, let me see. Yep, not a problem at all. All right, so Mr. Coley, let me see if I can find wrong email.
I had a little epiphany.
Mm-hmm.
I don't know how many classes you got and how many students you got. You have to answer a lot of emails.
I do, sir.
I was just thinking about it. I was like, he didn't respond back. So I'm like, then it dawned on me. I was a little slow. I was like, he got other students out there.
Oh, you funny.
They just hit me. I was like, yeah.
Oh, that's funny.
Did they answer any emails.
So you got X is, tell me if I'm writing the wrong one, let me know.
All right, let me flip to the page of my book. I said, since I sent you the attachment, I ain't had to flip to the page in the book, but let me.
Yeah, because I think you asked me about negative exponents.
Yep, that's it. That's the one right there.
Mm-hmm. So, what was that last thing you said before I get started?
4 attempts.
Oh, okay. Yeah. So this is the ones you say you really wasn't fond of because you're going to do use substitution. We recognize that we have this quadratic scenario again, this quadratic an equation that's in quadratic form because we have x to the negative 1 that's squared here, and then we have x to the negative 1 that exists here. And so if we let u be equal to x to the negative first power, that means our new equation is going to be u squared plus 7u plus 10 equal to 0. So anybody have any questions, feel free to ask. But that's we have an equation in quadratic form. We see that we have x to the negative first power here, and then in this first, or our leading term, x to the negative first power is being squared. So
But
whenever you
-2, right?
say that again?
Be a -2 exponent, right?
Well, that's what it was originally. But if you're talking about breaking it down or creating a scenario that would be easy for you to solve, you can break it up this way. Because remember, raising a power to a power, you're multiplying. So if I break it up this way, it's still the same expression, just that now I see that I have this and this. So now I have an equation in quadratic form.
They match.
Mm-hmm.
See?
Yeah. It's all about manipulating the problem so that you know whether it be that they match or so that you can solve it. Same thing as if remember we've had ones that had 2/3 for your exponent.
See, I didn't see that.
Mm-hmm. And so this would be the same thing, except I would break it up into 1/3 squared, and then 1/3 here. And once again, like you said, you're doing it so that these match. And that leaves this square out here, set me up for my quadratic form.
Thank you, Professor.
Not a problem, not a problem. So before I erase this, anybody holding on to this part? Anybody? All right, so let's go ahead and solve this. So we can solve this by, if we want to factor, that'll be u plus 5, u plus 2. Once again, if you're not cool with factoring, you always use your quadratic formula. Now we set each part equal to 0. Solve for u by subtracting 5 and then subtracting 2. But now we have to make sure that we remember that u is equal to x to the negative first power. So we bring that back in for u so we can actually solve. All right. Couple of different ways that we can handle this problem. I put a -5 here, it should be a 2. So if I wanted to get that negative exponent off of that x, I can raise both sides to the -1, because -1 times -1 is a positive. Yep. And so that's going to cancel out for us, leaving us with just x. And now, remember, these are exponents. So that's not -5 times -1. That's not -2 times -1. That's -5 raised to the negative first power. And so negative exponents will drop that 5 down into your denominator. And so the same thing happens here. Drop the 2 down to your denominator. And these would be your 2 answers. They have nothing to do, that's not negative. Negative turns positive. That negative exponent affects the 2 by dropping it down into your denominator.
If you see in my notes,
let me go back to it.
my attachment,
Mm-hmm.
it didn't dawn on me till late. I was like, I turned them all into fractions.
Yeah, trying to get to your problem. Yeah, you did that initially, right. And you have to be careful too. Now, that wasn't wrong to represent it that way, and you can solve it that way. But where you would have gotten the wrong answer, though,
And that's why I kept getting the wrong answers.
is that you took the 7 down with it. That 7, oh, you can rewrite this as this, but that 7 would stay up top.
See, I would have known that.
Yeah, because remember we talked about in last class, not last semester, you know, in 60, that in order for that negative exponent to be applied to the 7, you need parentheses. Other than that, the negative exponent is only applied to the x.
There's a lot of stuff to remember. All right.
Yeah, man, I know that. I know MDE 60 was a blur, so.
It killed some brain cells.
But yeah, so then what we could do here is, you know, multiply each term by x squared. And, you know, we actually talked about this process back in MDE 60 as well, but we don't have to revisit it. I already gave you that, you know, another way of doing it. So.
My head, that's why my head white now. I'm killing brain cells on this stuff. But thank you, Professor.
Not a problem. Not a problem.
It didn't dawn on me that x go to the bottom, and the other way is quicker than what I was doing.
Yep.
Thank you.
Not a problem.
I'll be hitting you up over the weekend.
I can't wait, sir. Hey, Super Bowl Sunday though. Super Bowl Sunday. I'm not gonna answer nothing on Sunday.
In the chat, when you moved the test, I was gonna chat Super Bowl. Thank God. So I got to hit you up on Saturday or Friday.
You say you got to get what on Saturday or Friday?
I got to hit you up on Saturday or Friday.
That's it.
But thank you.
Not a problem. You have a good one.
Thank you.
All right. Anybody else before we close out? Everybody good? All right. You guys have a great weekend. Be safe, and I will see you on Monday.